Hey everyone, so thank you and welcome to this first keynote speech, which will be delivered by Dr. Ahmed Mourad. So welcome, Dr. Ahmed Mourad. Thank you for joining and helping us with this keynote, and especially thank you for accepting our invitation to share your knowledge in this conference. So I would like to briefly introduce to everyone about Dr. Ahmed. Dr. Ahmed is a postdoctoral research fellow at the Information Engineering Lab, IE Lab, in the University of Queensland. He is currently focused on conversational systems in the context of agricultural domain. So it's very, very important and critical research that he's currently doing, and he's been a very, very fantastic researcher. I think without further ado, I would like Dr. Ahmed to start his speak. Thank you again, Ahmed.
Thanks, Jimmy, for the introduction, and thanks for the invitation. It's my pleasure to be here delivering this keynote. First, let me share my screen. So can you clearly see the slides?
Yep, it's perfect.
Perfect. Then I will start straight away. Thanks again for the invitation. My name is Ahmed Mourad, and I'm a postdoc at the University of Queensland and a member of the IE Lab research group. Today, I'm going to be talking about one of our current research projects. It's called GASK. And it's talking about a conversational agent that might help farmers in the field. To start with, why did we choose to focus on the farmers or the agriculture domain in specific? This is mainly because we are at the IE Lab research group. We really believe in applied research and driven by the local community needs. So just to give you a little bit some facts and give you an idea about the scale of agriculture in Queensland and the anticipated impact of the research related to this field. Queensland state has the largest area of agricultural land with over 30,000 businesses that contribute more than $10 billion to the state's economy. So it's a huge scale. So in the 21st century, as you might expect, there is plenty of data out there, a plethora of resources and data coming from research studies, from project reports, communications, scientific publications, and many more. And they are available for the farmers to make growing decisions and maximize the outcome out of their farms. However, they are not easily accessible. So for example, you cannot expect a normal farmer with a specific level of an education to be able to read a research paper and extract the information out of it. So is this conversational agent going to be useful only for farmers? Actually, there are three types of users that this research might serve and help. So the current practice is whenever a farmer has a problem, they either has faced it before, so they know what to do, or they might be able to go to Google or Bing and find an answer on the internet, just like the normal search that we do. Or a more common approach is they seek help from the professionals. So who are the professionals? We have two more types. The first one are the agronomists. Usually those are working to governmental organizations, and they provide support to farmers. And these agronomists have the technical knowledge and where they can read the research papers, extract information, or read reports, or actually they are the ones that generate the reports to help the farmers. And the last type of users are consultants, and usually those are from commercial companies providing pesticides and stuff like that. They can also provide help to the farmers. So what we do here is we develop a conversational agent called a GASK to help these three types of users. The figure that you see here, it provides a high level on how a conversational search agent might help answer a farmer's question. So what it does is, it gathers the information from different sources, like you can see here, from literature, magazines, and then it might contextualize the answer based on the soil type, for example, or based on the weather. Knowing the location of the farmer, it's able to extract this information, and then it presents the answers to the farmers in an understandable way. Whether it's going to be, for example, a specific answer, or it's going to be a list of suitable answers, and the farmers will pick the one that's suitable for them. So the question here is, why did we choose conversational search to address this domain, to address the domain of agriculture? The answer to this is that conversational agents have some unique characteristics that allow us to satisfy the complex information needs of farmers. What are these characteristics? So what we have here is an example conversation that might go between the farmer and the agent. So they have a problem with their crop. They have slugs, and they are asking what they should do. And as you can see here, the agent needed to know the location of the farm because they believe that the answer is going to depend on that. So the first property here is called mixed initiative, which means that either the user or the system can take the initiative to ask questions and steer the direction of the conversation. So for example, if you went to Google, Google will not ask you questions. When you enter a query, it will show you the results related to this query, regardless of the context. But in conversational agent, it's different. If the initial query is ambiguous, then it has the ability to ask a clarifying question to elicit more information from the user. And also, as you can see, we have here an iterative process of interactions between the user and the agent. And for this, the conversations are usually called multi-turn conversations. And the last thing is the memory. So a conversational agent will keep track of the entire conversation, and it can leverage this information at any point to contextualize or personalize the answer returned to the farmer. Now let's have a look at the typical workflow of a conversational agent. So we start here by the user submitting a query to the agent. The agent then tries to identify what is the intent of the user. So the intent could be, for example, that they are seeking information, or it could be that they are grading the system, treating it like a human being, for example, and grading the system, or could be giving feedback to the system, or some more extra intents. Then the next step is the dialogue manager. The outcome goes to the dialogue manager. This is the component that controls the entire conversation and decides what is going to be the next step based on the intent. So if it found that the query, for example, is ambiguous, then it will decide to ask a clarifying question. If it found that the query depends on the previous context of the conversation, then it will try to automatically rewrite the question to add all the required information to extract the answer. Or it might go straight away to try to find the document that might contain the answer, generate the answer or extract it from this document, and then display the result to the user using the same interface. The interface here can be text, can be audio, can be video, can be image. And based on that, the user will decide their next step, whether it's going to be answer a question from the agent. If they were prompted by a clarifying question, they could abandon the conversation, regardless whether they are satisfied or not. They could choose an option from a list of results that were returned by the agent, or they could decide to write a new query or just give feedback to the agent, whether they did a good job or whether they got something wrong and try to fix that and recover the conversation. So as an information retrieval group, we are going for this talk, we are going to focus mainly on the document retrieval component. So looking at the core relevance of a conversational search, it goes down to two types. We have single turn, which means a single interaction between the user and the agent. This is the building block. Or multi-turn, this is the more natural way where you have several interactions between them. For the single turn, we are sure that the user has only a single intent. For the multi-turn, we might have a single intent where the user is seeking to satisfy a single information need, while in multi-turn, they might have multiple information needs. So for example, they might ask for a pesticide suitable to treat a specific disease. And then, for example, they might change the intent to ask how to apply that pesticide. Again, for this talk, I'm going to be focusing on the basic one, which is the single turn, single intent for simplicity. And because also we are, as an information retrieval group, we are familiar with this setup, and there are plenty of data sets that will facilitate the research. The question now is which retrieval model to use. We have here two criteria. So in the x-axis, you will see that we have efficiency. A small value means that the model is fast. High value means that the model is very slow. This is the time that the model takes, the conversational agent takes, from the moment the user submits a question to the time that they return an answer to the user. And on the y-axis, we have effectiveness in terms of any evaluation metric. It could be precision, could be recall, could be any other information retrieval specific measures. So now going to the literature. So a common knowledge in the information retrieval community is that if you develop a model that has effectiveness within 10% difference from the state of the art, this is accepted by the standards of the research community. Another study by Google revealed that if you return the answer within 250 milliseconds or less, the user will be satisfied. If your system takes more than 2 seconds, this is not acceptable by any means by the user. So our aim here is trying to get anything less than 250 milliseconds. So now looking at the research on document retrieval, we have three main approaches. The first one is the bag of words. And what it does is basically it does exact search. So it takes the question, all the terms in the question, and try to find the documents that has any of these terms. And for many years, this has been the state of the art, and it was hard to beat. Of course, there were some extra features added to it, but at the bottom of it, it's exact search. And more recently, there are deep language transformers, which are based on neural networks, and they leverage large amounts of data to do training. And they had a huge improvements in terms of effectiveness, but as you can see here, at the cost of efficiency. So they are very effective, but they are very slow. And more recently, over the last less than actually 2 years, a third approach came out that's called dense retrievers, which we are going to explain shortly, that lies in the middle between these two. So it has better effectiveness than bag of words, although a little bit slower. and it has less effectiveness than the deep language models, but much more efficient. So our goal here is try to develop our models in this top left decision quarter, where we have a model that returns an answer within 250 milliseconds and has effectiveness that is not far from the state of the art, within the 10%. So one of the main limitations of the bag of word approaches is the vocabulary mismatch. So if the query, the original question of the user has some terms that do not exist in the documents, then you will not be able to link these two. So look at this example here. The user is asking about slugs. So their farm, their crop is affected by slugs, and they are looking for a treatment. And on the left-hand side here, we have a document, and then we do some processing to extract the main information from this document. So we will find that it's talking about the naturally occurring protozoa, and we deduce that it is effective for treating molluscus. So molluscus here are synonyms to slugs. So what we need to do, we need to be able to identify these two terms, and actually that they are synonyms to each other. So how did the exact match approaches solve this problem? They solved it using a specific technique called pseudorelevance feedback. So a typical pipeline in information retrieval is that you might have multiple stages, not only a single stage of retrieval, but multiple stages. At each stage, you are trying to enhance the quality of retrieval. So for pseudorelevance feedback, it starts with an initial retrieval. It returns a list of ranked documents. Then it assumes that the top K retrieved documents are relevant to the original query. And based on this assumption, they extract some keywords from these documents to expand the original query. So now you have a new query that has more terms, hopefully that they picked up the synonyms of the keywords in the original query. So the original query had slugs, hopefully it will pick up the molluscus as well. And then you do another round of retrieval and return a new list of the ranked documents. However, as I mentioned, there is an assumption here that the top K documents will be relevant. But this assumption is not backed by user judgment, which means we are not 100% sure that the top K documents are relevant. We do not have labels for these documents beforehand. So recent research tried to make use of the advancement in the deep language transformers, which have higher effectiveness than the bag of words or exact match. So they added here an extra layer, the neural selector, after the initial retrieval. So they do initial retrieval, they do re-ranking to re-rank the documents. Hopefully that will get better top K documents. Then they extract the keywords to generate the new query and do a third round of retrieval. However, the improvements were marginal, mostly marginal. And as we know, they are very expensive to use and inefficient. They take very long time. So obviously there is a trade-off here between effectiveness and efficiency. So for our research, we are trying to address these limitations. Sorry. So one of the reasons I forgot to mention here, one of the reasons for the inefficiency here is that the neural selectors has some constraint on the length of the input. So what you do here is you are trying to, how the neural selectors work, you got the initial retrieval and you have the original query. You are trying to feed into this neural network every pair of the query and the document to generate a score for the relevance, how they are relevant to each other. So if the document is much longer than the input size limit of the neural selectors, you will have to break it down into smaller chunks. So in our research, we're trying to address this limitation by exploring different techniques in how to break down the long documents. So the first approach I'm going to talk about here is called text-based pseudorelevance feedback. And what we have here, this is the collection of the documents that we have. It's saved into text format, obviously as from the title here. And we have BM25. This is a very well-known bag of words exact match information retrieval system. And what we do here, we have the query, input the query to our search engine, get the initial retrieval results. Then we do a re-ranking step using BERT. BERT here is the deep language transformer model. And then we get another re-ranked list. Then we pick the top K documents for our PRF approach. And then we try different text handling techniques that we believe are more efficient than the current practices in previous research. And then what it does is it breaks the document into several chunks, try to score every pair of the query and the chunk and or partition of each document. And then it aggregates the scores of all the partitions for each document to generate the final score. And then we have our final ranked list. The model that is based on this approach is going to be called BM25 BERT PRF. Another approach that we tried is vector-based approach. So here we change the representation of the documents. We are making use of dense retrievers. In specific, we tried two retrievers. One is called RipBERT and the other one is called ANTS. And the difference between these models and BERT is that they are separating the encoding of the user question and the documents that you have in your collection. So for BERT, when the user submits a query, you are trying to calculate the relevance between the question and the documents while the user is waiting. While in dense retrievers, they encode the documents offline beforehand, and they have them saved in the index. And then what they have to do at the query time, at the runtime, all what they have to do is encode only the question of the user or the query. So here you can see the model. We have our data collection. It's saved in a vector format. And then we have the query submitted to the dense retriever. Then it generates the encoding. We retrieve our initial list of the relevant documents, consider the top K documents for our PRF approach, and then generate the final result. The models that are generated from this model are called ANTS PRF and RipBERT PRF. So now let's look at some of the results that we had based on a single data set. It's called Trek Deep Learning for 2019. This is a shared task for the information retrieval research community. And looking again at our x-axis, we have efficiency and effectiveness, and they have our decision quadrants. So the black points here, these are the baseline models. So at the bottom left corner here, we have our exact match bag of words models. At the top right here, we have our, again, the hybrid between exact match and deep learning. And here we have our dense retrievers. Then we have our text-based approach where we apply PRF on top of BM25 and BERT. Then we have two models that were not presented earlier, and these are hybrid models. So they are using both the text representation and the vector representation. So they use the text representation for the BM25 BERT, and then they get the equivalent vector representation from our two dense retrievers. So one is based on ants and the other is based on RibBERT. And then we have our two vector-based models. So as you can see here, the sparse retrieval based on bag of words and exact match are very fast, but they are ineffective. They have the lowest effectiveness. And our both text-based re-ranking and our hybrid re-ranking models, they are very effective, but they are extremely slow. So the time that they take here ranges from 3.5 seconds to 30 seconds. And just a reminder, we said that the maximum tolerance for users is 2 seconds. While the last ones here, when we applied pseudo-relevance feedback to the dense retrievers, we were able to enhance the baselines of the dense retrievers. So they are more effective while not losing anything in terms of efficiency. So we are still in the happy decision quadrant here. So to wrap things up, what I have presented to you here is the work that we have done on the single turn conversations with single intent. Our next step is going to be how to generalize this framework and apply the pseudo-relevance feedback to the more reasonable setup, which considers multi-turn and that might contain single intent and multi-intent. So just to give you an idea about the extra challenges that are going to be introduced in this case. So we mentioned here the feedback. So here we have an explicit feedback. When the farmer started asking how to treat slugs, the system asked about the location, and they keep that in the memory of the conversation. And once the farmer accepted the answer returned by the agent, they informed the agent that they are going to try it later today. How the agent is going to make use of that, they have access to the location. So they realize that it's going to be raining. And if you know a little bit about agriculture, when you apply a pesticide and then it rains, it might not be effective. So it will customize the answer and recommend that they wait for a couple of days, then they apply the treatment. And this is a slide of our GASK team that's split between 3 different organizations. So it's UQ, it's CSIRO, which is the largest research organization supported by the government here in Australia. And we also got members from the School of Agriculture, and we got members from the government organization that supports farmers. Thank you for listening and happy to take any questions.
Thank you, Ahmed. That is a very, very insightful knowledge that you just shared. So now I would like to open a question from the participants. So if you have any question, please use the raise hand from the Zoom. Okay, I can see Joko is having a question, but hang on. As a privileged chair in here, I would like to ask a question. Okay, that's a privilege of a chair, right?
Please,
I can ask the first question. So I think it's a very interesting application of information retrieval to help farmers finding information. One question, is it applicable to other language? I mean, is it language specific? Can we apply to other language? If not, then, or if yes, how or how much effort will it take to apply to other languages, like Indonesian, for example?
Yeah, Sure. So it's a yes and no. So depending again on the models that you are using. So usually, for example, if you are using the BM25, the bag of words, it's applicable straight away, although you might need some extra pre-processing steps for the documents that might be specific to the language. So in this case, yes, some little extra effort. For deep learning, they are supposed to be language independent, but at the same time, if you use BERT, it has been shown that if you fine-tune the deep language models on the target domain and the target task, so the target domain in this case is agriculture, and the target task in this case, which is retrieval, and the target language, they has much better performance than if you didn't do these optimizations. So you can apply existing models. They still will get you reasonable results. But if you want the best results, you have to go the extra mile of adapting it to the language that you want.
Okay, got it. Thank you, Ahmed.
No worries.
Now, Dr. Joko.
Okay, thank you. I would like to ask about BERT. Yeah. So in your conversational bot, you are using BERT as classifier or something like to recognize the user question. Yeah. So BERT actually is a pre-trained deep learning model. Is correct? Yes.
Yeah.
Yeah. So my question in your conversational bot, it is need to fine tuning the weight of the BERT before you apply to recognize question in agriculture field.
Yeah, that's
it is
correct.
need to fine tune it. So if you need to fine tune, it is all layers or just in a fully connected layer that you need to fine tune the weight of the BERT.
Sorry, can you repeat the last sentence? The question.
Yeah, you need to fine tune the model so that can be recognized the question from the user in the field of agriculture. So my
Yes.
question: which parts of the BERT need to be fine tuned? All width of the all layers, or just in the final layer or fully connected layer that need to be adjusted? Yes.
Yeah, it's just the final layer. So what you do is here, you might actually have several rounds of fine tuning. So you have your original BERT model. Okay, as I mentioned to Jamie, you have the original BERT model. And the tasks that it was trained for is different from what we have in information retrieval. So you need first to fine tune it on the task because it was developed for next word, next term prediction. So when you give it a text, it predicts the next word or the missing word in the middle sentence, right? While in information retrieval, we are trying to rank documents to find whether a document is relevant to a query or not. So you need first to fine tune it on the task, on the downstream task, which in this case is document retrieval. And then you need to fine tune it on the domain dataset in order to be able to capture the most salient keywords and terminologies in the target domain, which is agriculture in this case. And these are not expensive processes. They are very cheap once you have the data set. So for information retrieval, for example, there was a huge data set released by Microsoft. And that's what everyone is making use of to fine tune it on the information retrieval tasks. And for this project, we then had to create our own data set, but a much smaller data set for the agriculture domain, which we are going to use to do another iteration of fine tuning. Did this answer your question?
Okay. Can I ask one question again?
Yeah, please. Go ahead.
Yeah. So the output of bird in your bot is the number. It is represent the ranking of the input query. It is correct.
Yes, the query with the document, a pair of query and document. So the basic idea in information retrieval, you have a query and you want to go against all the documents that you have in your data collection. In this case, for example, all the publications that you have in your data collection, and find which ones are the most relevant to the question. So you generate a score for each of them.
Okay, thank you.
No worries.
That's a very interesting question, Dr. Joko. So following up Ahmed's explanation, I'm just wondering, does it mean that you only include data collection specific to agricultural domain in your collection? In a sense, like there are many documents discussing about slugs, for example. Some people discuss how you can cook slugs, and surely you don't want that in your agricultural domain. So did you exclude all that?
Yes, that's a very good question. So part of the slides that I moved was talking about our data collection. So it's not a data collection from the public web. So what we did is we got lots of reports from the organizations that I mentioned that support the farmers. We got all the research publications from different libraries. We got some of the websites to agriculture. So everything is just related to agriculture. And we ended up having around 90K documents in our collection. Not the largest, but that's the documents that serve the local community.
Okay, thank you.
No worries.
Any other participants had any question? Anyone? Okay. Hang on. I do have one more question here. Is there a way if we can convert or use agent from Google or Amazon to somehow make it specific to a specific domain?
Google or Amazon did not release conversational agents, as you would expect, because they have their own conversational agents for Google Home and Alexa, so definitely they won't release that in public. But Facebook generated a framework that is called Parler, which means talk in French, or it's the English version is called Parle AI, which means talk artificial intelligence. So Parler is a conversational agent that you can deploy and play with out of the box, and you can customize and add more components.
Okay, thank you.
No worries.
So I think that's it. Thank you very much. So before now, I would like to wrap up or summary what Ahmed was sharing to us. So he's been sharing his work on helping farmers to get information on whatever that they're doing. They're trying to grow crops like a healthy one that is like they can bring more benefits to the farmers. And he's trying to help in a way that is what people normally do by using natural language to ask questions, using chattings. And the aim is to provide an effective, in a sense, it's accurate responses in a timely manner, which is very, very useful. And of course, we don't want to talk to someone that responds like in 30 seconds, like Ahmed mentioned. So it's a very challenging, yet it is very important. And we're actually looking forward if this one can be applied to other language, especially in Indonesia. So thank you very much. Thank you very much, Ahmed. It's been a very, very pleasing session. And I would like everyone to just give thank you to Ahmed. Thank you, Ahmed.
Thank you.
Don't
Thanks
leave.
for the
And
invitation.
after this the committee. Hang on.
Sure.
I think we do have a photo session by the committee. Thank you.
Thank you.